In this video, we'll talk about Euler tours and also how to Eulerize a graph. An Euler tour, which is kind of loosely defined here, it's not the formal definition, it's a traversing of the edges of the graph in which each edge is used exactly once, and you also have to start and stop at the same place. And what I mean by traversing is that you have to walk around the graph. Picture yourself as like an ant that lives on the graph, and you're walking from vertex to vertex, but you can only walk over edges. So you have to use each edge exactly once, and you also have to start and stop at the same place. So there's a famous theorem that was proven by Leonard Euler, and that's how Euler tours got their names, that says this. It characterizes when a graph has and does not have an Euler tour. So a graph has an Euler tour if and only if it has both of these properties. If even one of these properties fails, then there's no Euler tour. So it must be connected. In other words, you can get from any vertex to any other vertex, and all the vertices must have even degree. So we have a graph here, and if we just ask ourselves the question, does it have an Euler tour? Then to answer this question, does it have an Euler tour, not can we find it, but just yes or no, then we just have to look at these two conditions. We have to check if the graph is connected, and if you look hard enough at this graph, you'll notice that you can get from anywhere to anywhere, so yes, it is connected. So it passes that part of the test. Yes, it's connected. Are all the vertices even degree? And we have to say no. And here is one vertex in particular that has odd degree. I don't have to find all of them. All I have to do is find one. And if it's true that one of these does not have even degree, because it has degree 3, then it fails. So our answer is no for the even degrees. And since it fails at least one of these, our answer is no. There's no Euler tour in this graph. So this is where the idea of Eulerizing comes in. So since it doesn't have an Euler tour, we want to kind of modify the graph. And that's this process of Eulerization. Eulerize the graph. And what this means is add edges until the graph meets, the new graph that we create meets both of these conditions. So we have a connected graph and all vertices are even. Since our original graph is connected, we don't have to worry about that. So we want to add edges until all vertices have even degrees. So the first thing we need to do is identify all the odd degree vertices. So we found one here. Here's a degree 3. This is degree 3. That's 2, that's fine. 2, 2, 1, and 2. So these are the vertices of odd degree, the ones that are circled. So those are kind of the problem vertices, and those are what we focus on when we Eulerize the graph. So I want to add some edges. So what I want to do is add also the fewest number of edges possible. So since we have 4 vertices of odd degree, the best we could possibly hope for is adding 4 divided by 2 edges. So in other words, 2 edges. Adding 2 edges is the theoretical best that we could do. So if we can get away with adding 2 edges, then we've Eulerized the graph in the minimum number of edges possible. So the best way to do this is to look for vertices of odd degree that are not connected to each other. So for example, not this pair, because I can't add this edge unless I add a multiple edge, and that's a slightly different type of Eulerization. However, these two are not connected. So if I add this edge, that's supposed to connect to that vertex, if I add that edge, now each of these vertices has its degree increased by 1, and it was odd, so now it's even. Right, see this one has degree 2 now, and this one has degree of 4. And so those are fine. We can kind of cross those off our list. And then if I can add this edge between these two vertices, well, now I fix that problem too, because I have degree 4, degree 4. So then we're done. So we have Eulerized this graph with 2 edges, and since 2 edges was our theoretical minimum, and we did that with 2 edges, then we've done it in the minimal amount of edges. So that's Eulerizing a graph when you can't use multiple edges. If we were allowed to repeat edges, then we could have just added this one twice, but this is a different procedure. And so that's Eulerization.